Good afternoon and welcome to Advanced NMR Spectroscopy Lecture 3. So today I will repeat or I will summarize whatever I have taught in last two lectures, and I will use the board today so that try to make the things understanding much more clear. So what we have learned that, so we'll consider only a nucleus with I equal to half and gamma is equal to positive. Okay, for example, 1H. Okay, for example. So what we have seen that when you put such nucleus in a magnetic field, we see I will show you the Zeeman splitting. So this is your energy axis. This is your magnetic field P0, and this level is called alpha. This level beta, we call this as a plus half. This is minus half. These are the MI values. And the population here is N alpha. This is N beta, and N alpha is greater than N beta. Okay, so now we'll see that how to record NMR. So now I'll draw a coordinate system. This is our Z axis. This is our X axis. This is our Y axis. Okay, and now I'm putting the external magnetic field around the Z axis. And if you see that I will now draw the axis so these are our individual magnetic moments. क्या हो गया? Okay, don't worry. Okay, and so these are the individual magnetic moments excess in alpha minus n beta, which I have shown here. Okay, these are the excess over the n beta. Okay, now if you see how to use the different color,
go down.
Okay, so I can, okay. So these are, so I'll select now. So these are the individual magnetic moments. Now if you see that, so they are precessing around the magnetic field, that is omega 0 is equal to gamma B0. Okay. Now, if you see there the Z component magnetization, if you see, now let us see how this magnetization, we will see a magnetization along the Z axis. We call this as a MZ here. This is the vector sum of all these components. We call this as a MZ or simply M. Now, if you see the XY component magnetization, so this is your XY plane here. Because these pins are randomly oriented, so you will see that all these, although if you consider each magnetic moment, they have a XY a component, but if you consider them in total, you will see that the xy component magnetization is equal to 0. Okay, so now if you want to see the NMR, what you have to see, we have to see these spins, extra magnetization. So how to detect that extra magnetization? Okay, so that is the next thing we have to do, because now if you want to detect this extra magnetization, you have to bring a detector. Now you cannot put the detector along the z-axis because you have the external applied the external magnetic field is applied in that direction. It is a very strong field. So if you put there, it will interfere with the detector. So we have to put the detector somewhere in the xy plane. You can put in the y-axis, you can put in the x-axis, or anywhere in the xy plane. And if you put the detector at xy plane, that means you have to somehow bring this magnetization mz into the xy plane or some component of it for the detection. Now how we will do that? So for that, what you have to do, you have to put a radio frequency field, a radio frequency field. What type of radio frequency field? It is a rotating radio frequency field. Apply rotating radio frequency field in the xy plane. Okay, with magnitude of b1. Okay, so the radio frequency field, so when there is a resonance, this radio frequency field, that omega rf will be equal to omega 0. So under that condition, what you will see, that if you apply now the radio frequency field along this, let us say along this x-axis, the B1 field with radio frequency, with frequency of omega RA, and when it matches with the precessional frequency of this nuclei, at that time what will happen is all these spins, they will undergo a phase coherence. So when these two matches, you will see a phase coherence. You will see a phase coherence among these. Next. So what you will see is that, so again I will draw it here. So now due to the phase coherence, when you are applying a, now we are applying a B1 field. This is your B1 field with omega radio frequency equal to omega 0, and you have the magnetic. Now you will see that your all those magnetic moments, they will undergo a phase coherence, and so your the you will see your will now be tilted. Okay, so under this condition, you will see that, and that angle is called the alpha. So this alpha depends on the magnitude of B1 and duration it has been applied. Okay, now see, previously when there was no B1 field, the magnetization was along the Z axis. Now because of this, you can see a so you will see a component of this in the XY. You will see a component in the XY plane. So this will be your MXY component. Okay, so previously, see, before you apply the radio frequency, the XY component was 0. Okay, now you can see because of this coherence, the magnetization tilted, and now you have a MXY component, and you, as you put your detector in the XY plane, it will detect this magnetization. So you get a signal, and that can be detected. So this is called the resonance. Okay, and this MXY is equal to M sin alpha. This M is nothing but your the M is your equilibrium Z component magnetization that we saw before applying this radio frequency, which you saw along the Z axis. Is it clear to all of you how we are getting the resonance condition?
And unmute. Tell participants they are unmuted so you can.
So we are applying a rotating magnetic field BOR, rotating radio frequency magnetic field in along the B1 along the x-axis. Okay, and which is rotating, the frequency is omega RF is equal to omega 0, that is nothing but the precessional frequency. Under such conditions, all the spins now they undergo phase coherence, and you the magnetization now gets tilted, and which is now shows its MXY component, and you can detect, and you can tell how much of what will be the magnitude of MXY component. You can find out from the alpha, that angle, and that M sin alpha, and this alpha depends on the amplitude or strength of the B1 field, and as well as the time or duration it has been applied. Okay, now if you see that under these conditions, now we see there are three components rotating. You have the B1 is rotating with, which is equal to omega 0. Second, you see your XY component is also rotating with omega 0. And of course, the M is also, now M, the tilted M is also rotating omega 0, because all these things are happening, these two last 2 and 3, they are happening under the applied magnetic field B0. Okay. So if you see, the issue is here that there are several rotating components. Okay. So when there are several rotating components, you will see that it brings complexity in the analysis of the signal. Okay. Suppose under these conditions, what you will see, suppose under this condition, how the magnetization will appear. Let us say you have the magnetization. I'll show it here separately. I will draw it. This is your y, this is your x, this is your z. Now you see you have the, let us say, when you tilted the magnetization by little bit. So initially it was here. This is your M, and now you tilted it little bit. So when it is along the z axis, you will see there that apparently as if it is not rotating. It is rotating, but see, it is along the z axis. So you will not see, there is no apparent rotation. But if you tilt it little bit, which we are doing it here, so what you will see during, as you have tilted it, so what you will see that, we'll draw with a different color. Okay, so as you have tilted it, so it has now moved to this position. So it will start now processing. So what you will see, you will see because see that magnetization is rotating at a speed of omega 0. Okay, and your applied field is rotating. So there are two things. One is that the applied magnetic field is rotating it in this direction with a velocity of or frequency of omega 0, and another, this is in the and another is rotating in this direction, okay, with a frequency of omega 1. So if you combine both of them, you get a spiraling type of thing. As the magnetization move from z axis to xy plane, you will get such kind of spiral thing. So it makes a very complex situation to analyze the signal. I hope it is clear. Any doubt from anybody? Okay. So
box you can see sometimes. Chat box you can see.
Any doubt so far? So
You can.
So due to, you can see the complexity, because there are now two rotating components. One is due to your applied magnetic field B0, applied magnetic field B0, that is giving you omega 0, and this is coming from your applied B1, because they are B1 and B0 are in perpendicular direction, so their movement are also perpendicular. Okay, so you are getting a spiraling kind of situation, a complex rotating situation, so that makes it very difficult to explain mathematically. So let us see what next we should do. So we are introducing, now we are bringing a mathematical trick. You know, it is just a mathematical trick. So previously it was our laboratory coordinate system, laboratory static coordinate system. Where we have seen three types of motion. Okay. Now we are doing a mathematical trick and moving to a rotating frame coordinate system. Okay, so in laboratory frame, it was like this. Your this is your x, this is y, and this is your z. Okay, and so these are static, and motions are happening around these three coordinates. Now in rotating frame coordinate system, what we are doing, so these are your static coordinate system x, y, and z. Now we are rotating this coordinate system so that is along this only. So this is your x prime, you will call this as a y prime, and this is z prime, and these coordinates are rotating at the same frequency omega 0, which is nothing but gamma b 0. Okay, so this is the speed or the rotational frequency of this coordinate system is equal to the precessional frequency of the nucleus we are trying to observe. So what you will see under this condition, you will see that your xy component will also not will be static, your m will be static. Okay, now if you put your b1, now we are putting b1 field. Okay, so we are putting a b1 with a rotational frequency, the radio frequency, rotational frequency is omega RF. This small RF is called the radio frequency. Okay, so we'll call this the rotating frame frequency omega RF. RF is the rotating frame equal to omega 0. Okay, and when there is a resonance condition, you will see that omega 0 is equal to omega radio frequency equal to omega RF. Clear? So now you see, now suppose a observer who is standing outside, what you will see that still he will not see now relative motion of but he will see the whole system is moving. Now suppose let us say if the person who was initially standing here, okay, now he is coming and sitting on this. Okay, he will just let us say standing on the y prime axis. Okay, y prime axis. So what you will see now, everything is stationary. The b1 is stationary, the mxy is stationary, the m is stationary. Okay, so by moving from laboratory static coordinate system, when we move to rotating frame coordinate system, we will see that same thing are all these rotating things are becoming stationary. So your mathematical analysis becoming simpler. So you see, this moving from laboratory static coordinate system to rotating frame coordinate system is a mathematical trick. Okay, it is nothing that like something is rotating, or it is not like that. It is a mathematical trick to simplify when there are complex movement systems. So now let us see. So we saw that b1 is now stationary, b1 is now static, mxy is static, okay, and m static. Okay, now let us see what happens to okay, so that has not yet been addressed. Okay. So what you'll see in the rotating frame, in the rotating frame system, the M, the magnetization along the Z axis, it does not feel the full effect of B0. Okay. Rather, a reduced, I will tell you reduced, okay, magnetic field B prime. Okay. Now you may say that why it is feeling the reduced field. Now you think something like that. See, before your let us say before your in the laboratory coordinate, what you saw? You saw the precessional frequency is omega 0. Okay. Now you started rotating the frame. So what you will see, you will see the omega 0 is also decreasing. As your frame is rotating, relatively you will see the omega 0 frequency is also decreasing. So when this omega RF rotating frame will become equal to omega 0, what you will see? The omega 0 will be equal to 0, as if there is no movement. So what that tells? As if omega 0 is 0, that means omega 0 comes from gamma B0, and gamma cannot be 0, so B0 will be equal to 0. That means when the frequency of rotating frame frequency is equal to the precessional frequency, virtually the external applied magnetic field disappears. Okay, it is not, you are not as if not that you have switched off the B0. It's just mathematically it disappears. Okay, so now what is the only field? You see, now you have the B1 field. You have the B1 field which is perpendicular to Z axis because it is applied along X prime axis. Okay. So now only if you see, the only effective field here is the B1 field. Okay. So what will happen now? The magnetic moment. So I'll draw it here now. This is X prime. This is Y prime. This is Z prime, and this is your B1 field. This is your B1 field, and now you have the so you have the magnetization. It was here. Okay, so now what it will do? It will start precessing in this direction. Okay, because of the B1 field. And what will be that frequency? Okay, so under the condition when B0 is equal to 0, under the exactly resonance condition, so you will see that this is rotating. Okay, clear? So now let us see suppose so let us now go see. It may happen that that you will not be always the omega 0 is equal to rotating frame frequency. There will be situation where omega RF will be slightly different from omega 0. That means under that condition the B0 will not be 0, and that will be your B prime. So we call that as a reduced magnetic field. Is B prime equal to nothing, so it will be the B0 minus, due to the relative motion we are getting, so that will be your omega rotating frame frequency divided by gamma. Okay, so if omega rotating frame matches with omega 0, then you will see that the B prime is 0. Okay, but they are under certain conditions where they are not perfectly matching. We will see many times they are not perfectly matching. So there will be some. So this part is called a fixitious field, and that is originated due to the relative motion of the coordinate system. So now if the B prime is not 0, now you have one field is B prime, another place is B1. Now these are the two fields you are getting. One is your along the Z direction, this is along the Z direction, this is along the X prime, this is Z prime direction. So what will be the effective field? So B effective will be equal to, what will be its magnitude? Will be B1 square plus B prime square. Okay, the magnitude. Okay. Okay, and what you see now, you have this, so this will be your now B dash, and this is your B1. So automatically now, because these two are vector quantities, so where it will lie? So okay, so we'll see that I'll just draw only two coordinates now. This is your X prime, this is your Z prime. Okay, and you have you have the B1 here, you have the applied B1 here, B1, and you have the B prime. Whatever it is, it may be now B prime will be, it can be 0 also under certain conditions. So what you will see, because these two are the vector quantities, so what you will see that no, sorry, I'm drawing the okay, just a minute. I'm drawing this. This should be, I think, in earlier drawings also. Now, this will be the direction of the field, because I was wrongly. In earlier drawings also, it should be in this direction. Okay, so what you will see, a B effective. So you will see a B effective. B effective. Now this B effective, the angle, this B effective angle theta will depend on, so tan theta is equal to B1 by, this is just by simple trigonometry. Okay. So now the question is that, see now once the B effective is there, then your magnetization, you have the magnetization here. You have the magnetization was here. You have this magnetization M. Okay, so now this will start precessing around this B effective. So if it presses around this B effective, you will also have XY component. Okay. But this, what we have to do, that's why if you want to, if you want the best possible resonance condition, the B effective should lie almost on X prime axis. Okay. Well, that means B effective should be equal to almost B1. Okay. So if you consider the some mathematical things I have already told you, but still I write it here, that tan theta in terms of rotational frequency, tan theta is equal to B1 is B1 divided by this B prime. B prime is nothing but, if you do little bit of mathematics, you will see 1 minus omega RF rotating frame divided by omega 0. Okay. So now there could be two possible conditions. Okay. So one possible condition is that omega RF, okay, and omega 0 are very much different. So omega RF can be less than omega 0. Another case, omega RF can be can be greater than omega 0. In such cases, you will see that the B effective will prefer to be either, in this case, it will be aligned close to Z prime axis. Under this condition, it will position around very close to minus Z prime axis. Okay, so either it will be, so theta will be, in this case the theta will be equal to 0. In this case the theta will be equal to 180 degree. You can mathematically, you can find out from the equation. Okay. So when this omega rotating frame is equal to omega 0, you will see that tan theta is equal to infinity. That means theta is equal to 90 degree. That means it lies along X prime axis, and that happens when B effective is equal to G. Sorry, B prime equal to 0. Okay. So now the question comes, why we have to keep this B effective very close to X prime or on X prime or in the XY plane. Okay. See, if it is not there, then you will see that the problem is that you will see that now this magnetization will presses around this B effective with, so you will see that B omega effective will be equal to B effective gamma. Okay. So this will presses around this. Okay, but the main thing is that then you will see the extent of magnetization in the XY plane will be much less. So the sensitivity of the experiment will be much lower. So this part is clear. So what we have to do, that we have to, that's why your rotating frame frequency should match with the precessional frequency. In that case, the B effect, the B prime will be very close to 0, and then your the field will be, now the B1 will be the most active field, and your magnet and the magnetization will move presses around B1. Now let us see. So previously what we saw is that your magnetization was precessing here with omega 0. Okay. Now what you see is that okay, now you are putting the B1 in this direction. Okay, so what you will see that your so if you put now you do not have your B, this is your P1, what you will see your magnetization here will start processing in the, so it will process in the okay. So now let us see how we detect the NMR. Now let us see how to see the resonance. So when this omega rotating frame is equal to omega 0, your effective field B effective is equal to B1, and corresponding frequency is omega 1 is equal to B1 gamma. Okay, so now so once you apply the B1, so this your magnetization will now move to, so when this magnetization moves from Z prime, M moves from Z prime to Y prime axis. Okay, so that is nothing but a angle of pi by 2. Okay, so we call this as a, so this is one situation, it can move, and if you, so it depends on the B1, you can see B1, okay, it depends on the B1 and how much time and time. Okay, so we can consider that pi by 2, this is the angle, will be equal to omega 1 t. Okay, so you can find out how much time it will take. Okay, so this is the time required for, so if you similarly if you keep for longer time, you will see that it will be coming to, so it can move up to, it can go here. See, it is rotating, it is not that it just stopped there. So we are giving the B1 fields for a particular time so that it reaches to y-axis. Okay, or if you give enough time, it will reach to, it will give you pi. You got this as a t1, we'll call t pi by 2, we'll call this as a t pi. Okay, so similarly if you keep it for further, it will keep on moving. Okay, because it has a rotational frequency of omega 1. Now let us see in continuous wave NMR how we detect the, how we get the resonant condition, and how we detect the so in CWNMR what you have seen, you have the M will be, there will be, it will be M1 plus M2 plus M3 plus, so there are many nuclei. So what you do, you have now the rotating, so your all these things are here, and this is your B1 field, this is your, okay. So what you do is that you now keep the B1 fixed. Okay, so the nuclei which is coming under now resonance will be now tilted and detected. Okay, as soon as that resonance, so as soon as this matches with this, you will see that component which is matching with this, because we will be using a very weak B1 field. Okay, so as soon as it matches with this M1, that those nuclei will be tilted and will be detected, and as soon as it passes that resonance, you will not see any signal. Then when it comes to M2, you will see like that. So by this way, if you change now the B0, okay, slowly, so that all that, because you can change B1 also and B0 also, but if you keep the now we are omega RF, I will call that RF is equal to omega radio frequency. So you can keep the radio frequency constant, change the B0, so that slowly all nuclei will come under resonance and you can detect it. Okay, or you can keep the B0 constant and keep on changing the radio frequency, so that all the nuclei will come under one by one resonance, and that is the way in continuous NMR done. But let us see what is pulse NMR. Okay. So now pulse NMR is nothing, but now we will be, so let us say in pulse NMR, what we will be doing, we will giving the B1 for a particular time, B1 pulse for a particular time, so that it will rotate by pi by 2. Okay, so that is only thing that I have already showed you here. Okay, so that is called the pi by 2 pulse. Okay, so we can call this as a or if you consider this as a alpha is equal to omega 1 pp. Okay, or you can consider this as a gamma b1 pp is pulse duration, and this alpha, if you know that pi by 2, you can find out what should be the TP. So you can find out what should be the time required to get a pi by 2. So you have to give a pulse for that much time only. Okay. Now normally what you see that this and now as I so this is very simple when you have only one frequency or only one type of nuclei. But suppose if you have a large number of various type of groups of nuclei, so this is called the on resonance condition. If you have only one frequency, you can come under, so you can apply the omega RF is equal to omega RF is equal to omega 0. Okay, so that your B effective is equal to B1. So, and it will lie along the x axis. Okay, but when you have a many nuclei which do not have the same resonance frequency, then you will have the difficulty. So let us see. So so it may be that it is on resonance for one particular set of nuclei, but then it will be off resonance for other nuclei. So automatically you will have a B effective there. So in case of multiple group of nuclei, you will always have a B dash, and B dash will not be equal to 0. Okay, so automatically under those conditions you will have a B effective. Okay, you will have a B effective. Okay, so now as I told you, the B effective, if you bring it to very close to the xy plane or along the x prime axis, then you will see that you will get the full strength of the signal. That means your B1 should be very strong. Okay, let us okay, ठीक है, इसको we can use it. Okay, now let us say you have a, so so what we have seen is that you have the 5 minutes আছে না? So now I'll go to this as I'll make this as a x prime. This is your z prime. Okay, so now we have seen that we are applying the B1 here. Okay, you have the B prime here, and you have a B effect. Okay, so now we have to choose a B1. Okay, we have to choose a B1 so that the B effective will be either at x prime or very close to x prime. Okay, for example, let us see. Normally the B1 is given in kilohertz. Okay, now where from this BR, you see when you use NMR machine, you will see the B1 is given in kilohertz. It is nothing but it is the omega is equal to gamma B1, okay, divided by 2 pi. Okay, that is actually gives you the, so that's why this B1 unit is given in kilohertz. That is nothing but this. Okay, so normally you will see that B1. Okay, so there, so if you give a hard pulse, we'll call now a hard pulse. Okay, so hard pulse, the B1 will be very strong, or amplitude will be, okay, so that normally you will see about 30 to 40 kilohertz. Okay, so when it is 30 to 40 kilohertz, it will be coming in millitesla, milli, or less than millitesla. Okay, and if you see your B1 prime, so B1 prime coming from your offset, so you have a spectra where all the frequencies are not coming, you cannot bring them together, all of them cannot be resonance at the same time. So there will be a difference, either they will have lower rotational frequency or higher rotational frequency, so we call them as an offset. Okay, so that B1 is contributed, sorry, B prime is coming from offset. Okay, so, and normally we have seen in a proton NMR, if you consider this is around 10 ppm, so even in a 500 megahertz, it is 5000 ppm. Okay, sorry, 5000 hertz, and if you put the your central frequency, the B1 omega RF is equal to, at the middle of the spectrum, you will see a offset of around 2.5 kilohertz. So your B prime is around 2.5 kilohertz. Okay, so now you can find out what will be the B effective. B effective will be about, let us say you consider the 40 kilohertz, so it will be 40 square plus we'll put it for simplification 3 square is equal to, it will be 16,009. Okay, and that is very close to 40. Okay, and now what will be the tan theta, the angle? Tan theta will be 40 by 3 is equal to, we will call that 13.3, and you will see theta will be around 86 degree. Okay, so 86 degree is very close to 90 degree. Okay, so that means the B1 is, this B1 is strong enough to excite all nuclei almost equally. Okay, so this is the only thing you have to understand. So the B1 is now effectively lying very close to S prime. Okay, so that all the nuclei although they have offset, now they will be getting equal amount of radio frequency field. Okay, so they will not none. See, if it is less than that, then if it is B effective is not very close to expect, then they are getting different extent of B1 field. So the main problem is that still you get the spectra. There will not be any problem, but then you will see that the relative population of them will be different. Okay, so that means you cannot integrate the spectrum. Okay, you cannot compare the group of protons until unless all of them come to very close to X prime. Okay, so that was the only thing. Last class, I think there was little bit doubt. Okay, now as you will be putting this hard pulse for a, let us say for my see in a 500 megahertz machine, you will see that this pi by 2 pulse requires about 8 microsecond. Okay, 5 to 10 microsecond. You can find out what will be the you can find out what would be the uncertainty in frequencies. You can also see that you can generate the all frequencies needed to excite all the protons which are present in the offset, okay, or which are processing with offset frequency. Okay, so you can find out from this from 8 microsecond. So it is 10 to the power minus 6. So it will come around 20. You will see that coming around 20 to 25 kilohertz. You can get a frequency uncertainty of 20 to 25 kilohertz. Okay, so that covers your entire spectrum many more times. Okay, and that I have shown you. I'll show you. This is on resonance pulse. So this example I have shown you on the other day, same thing. Now you can see the you can getting during about you have a, or you need only around 2500 2.5 kilohertz of uncertainty, but you are now getting around 20 to 25 kilohertz uncertainty. And you can see the, if you use a hard pulse, you will see the excitation profile almost very similar. Okay, so there will be a there you will get a almost equal signal strength from all possible nuclei, although those who are even rotating with offset frequency. Okay, so now this is for hard pulse. Suppose sometime you need a very soft pulse. Let us say you want to do a decoupling of CH3 C double bond O CH2 and CH3. Okay, so this is, you know, this come, I'll later on I'll come to know. So this comes as a, some kind of 4 lines quartet. It will see as a triplet, and this chemical shift also I will tell you 4.2 delta. This comes around 1.4. Okay, approximately this comes around 2.1. These are the chemical shift positions. Now if we want to do a double irradiation or decoupling experiments, let us say we want to do a decoupling experiment here. So what kind of pulse I will use? We cannot use now a very hard pulse. Okay, because if you use very hard pulse, then this will also be affected, this will also be affected. So we need a very selective frequency. Okay, so for that we use soft pulse. Okay, soft pulse, you will see the B1 will be around 2 to 3 kilohertz or less. Okay, and also you will see the pulse duration is also around 1 to 100 millisecond. Okay, so previously you were doing microsecond. Now we have come down to millisecond. So you have reduced the B1 field, you have increased the TP. So automatically you see the excitation profile here. The excitation profile is it will selectively excite a particular group of nuclei without affecting the others. Okay, so For regular recording of NMR, you need the heart pulse, okay, so that it will excite all the nuclei uniformly. When you want to do a decoupling experiment or saturation experiment or selective saturation, you have to use very soft pulse, and for that you have to reduce your B1 field strength and also increase the duration of your pulse duration, so that you will get a very small range of frequency you can excite, so that you can selectively decouple and you can see what is the effect. You can do a decoupling, you can do other many more experiments. Those will be discussed when you study other things. Okay, so the rest of the things I have told you, I think that is no difficulty in understanding. This was the part which was not very clear to you according to me, so that's why I have repeated it. You go through my earlier presentations, and if you still any difficulties, you can inform me tomorrow, and then tomorrow I'll start a new thing, the chemical shift. Okay,
and tomorrow lecture at 5 o'clock.
And tomorrow lecture is at 5 o'clock.
5:30.
Sir? 5:30. Achha, tomorrow lecture is at 5:30. Okay, so 5:30 to 6:30. So you can tell me if you have any difficulties still, then I can again repeat, because this is a very important thing. You should know it because it will be useful for when you go for 2D and other things. Only thing is that my first few slides, I draw the wrong direction of B1. I'll just correct it for your record. Okay. बिगिनिंग को एक्चुअली इसमें है ना, इसके लिए प्रॉब्लम हो रहा है. इधर तो किया है ठीक.
First slide, first and second.
हाँ, so this ना,
this B1 arrow should be.
Yeah. Yeah, I have done this correction. Here also, B1 direction will be. I think here I have drawn correctly. There, I think some places. Yeah, it's okay.
The chat box is open, no? Or even unmute if they want to ask something.
So if you have any doubt, you can ask me, or if you have any, you can ask, send email, or in the next class. Okay. See, this is a repetition of your last two lectures, the important points. Okay, where I feel that you might have difficulty in understanding.
So attendance. Register your attendance.
And please register your attendance.
In the chat box.
In the chat box, you can put your registration number. So if there is no question, you go through the my lectures, okay, and also today's notes, and then we can again discuss later on. Okay. Thank you.
Okay, thank you very much.